Okay, so here we are. We've now calculated what we expect to see. Now, it's a little bit different than when we had the mean and we expect the sample mean to be close to the population mean, and then we looked at the difference, say, between x bar and mu, and to test our hypothesis, and we said, okay, to really understand this, we need to divide by some sort of measure of the standard error, and then we compared that to whatever it was, minus 1.96 plus 1.96, depending. Here, this difference between what we expect, this is what we expect, and what we've actually observed, turns out to have 4 components. We've got 4 cells. So that makes it a little bit more complicated than just a single number that measured the distance, how far away we were from the null hypothesis, if this was hypothesized mean. So how do we do that? Well, let's look at this. What we could do is look at this difference, and then look at this difference, and then look at this difference, and then look at this difference. Now, unfortunately, the same thing happens here as happens with when we introduce the standard deviation. We can't just look at those differences and average them out, because they would always sum to 0. So once again, we can square them. So look at the squared differences. Okay, that makes sense. And then we can sum those up and look at what happens there. But it's not quite satisfactory, because look at this cell here. This cell and this cell, they're roughly at 300 or so, 200, 300, something like that. Whereas these are at 2,000, 3,000, so they're 10 times as big. So a difference of 10 here, let's say, in this cell, is not the same as a difference of 10 in that cell. So we need to normalize. And so how we're going to normalize is the trick. And that is how we develop this statistic. It's called the x-squared statistic. It's going to take the sum over all the cells of the observed minus the expected squared, so that they don't sum up to 0, divided by the expected. There it is. This thing is called the chi-squared goodness of fit test. This is the x-squared statistic that gets compared to a chi-squared distribution, and just as with the t, we need degrees of freedom, and degrees of freedom are calculated as the number of rows minus 1 times the number of columns minus 1. In this case, it was a 2 by 2 table, so it's 2 minus 1 times 2 minus 1, which is equal to 1. And the reason why that is because once you fix one of these numbers, then you can get this one here by subtraction, because they have to sum up to 2850, and then once you've got those two, then you can get this one by subtraction, because it has to sum up to there. So you've only got 1 degree of freedom is what it boils down to, but it doesn't matter. You don't have to understand that. Okay, so there it is. There is the chi-squared goodness of fit test. It looks at the observed minus the expected in each cell. We're going to take the sum over all the cells, take the observed minus the expected, square it, and divide by the expected. That makes all the cells comparable to each other, so just sum up over all the cells. Now, having taught you the rule, let me teach you the exception. I'm sorry. But in this, just this one situation, when it's a 2 by 2 table, we'll see that we'll expand this to more than 2 by 2 tables. But for the moment, suppose you have a 2 by 2 table. We get a better approximation if we apply the continuity correction factor, which is you take the absolute difference of the observed minus the expected and then subtract a half. That's no big deal. The state is going to do all this for you anyway. But let's see, if we were to do it by hand, what would this look like? It would look something like this. So the 1 cell had 358 minus the expected value of 287, and then subtract another half, square it, and divide by 287. And then do the same thing for the second cell, and then do the same thing for the third cell, bottom left-hand corner, and so on. You do it for all 4 cells, and here we got 37.95. So this 37.95 is an idea of how far these expecteds are from these observed. How far are the expecteds from the observed? And it turns out to be 37.95. It doesn't really mean anything, but we just compare this to the theoretical value, and in this case, if we were to look at a table, this is what we would get, and then the p-value is less than 0.001. If we go straight to Stata, there it is, CC, so it's a case control, and I means that it's immediate, so I just threw in the 4 numbers from the cell, and there they are. And Stata spits out this, and there's the chi-squared, and it's 37.95, same as before, and the p-value is, the previous slide was an approximation. Here it says the p-value is 0.0040 zeros, which is their cute way of saying it's less than 405. Okay, because otherwise, if it was greater than 405, this would be a 1, and it's not, it's a 0. So this means that it's less than 0.405. But anyway, there it is. And you can see, you get all this extra information. There is the proportion of the cases who were exposed, and there's the proportion of the cases of the controls who were exposed, and that looks too different. But there's your p-value.